September 2008. A concrete slab on a tiny Pacific island. A rocket that has failed 3 times. A founder whose $100 million fortune is nearly gone, split between this vehicle and a dying electric car company. No customer will trust this rocket with real cargo. The mass on top is a dummy. This is Falcon 1's 4th flight, and it was never supposed to happen because the money only covered 3. If this fails, SpaceX vanishes. How any of this came to exist starts with a question almost nobody in aerospace was willing to ask. On Amalek Island, a remote strip of land in the Kwajalein Atoll, theory gives way to brutal logistics. There are no sprawling gantries or thousands of spectators here. A handful of engineers work in the humid Pacific air, surrounded by salt water and corrosive sea spray. They prepare a single 68-foot rocket. The operation looks remarkably small, almost fragile, lacking the industrial scale of traditional aerospace. But this is the 4th attempt. Beneath the quiet routine of the launch pad lies a silent financial emergency. The funding for a 4th flight does not exist on paper. Every dollar keeping this island base active comes directly from a single, rapidly evaporating personal fortune. That same capital must also keep a struggling electric vehicle startup on life support. There is no safety net, no corporate backing, and no room for error. The team works on a razor's edge, knowing that a single mistake will force a choice: which company survives and which one goes dark. In June 2000, the founder is ousted as chief executive of the online payments company that will become PayPal. Watching from the sidelines, he turns his attention toward space, concluding that government bureaucracy, rather than the cost of physical materials, is the primary barrier to affordable spaceflight. Legacy aerospace relies on a sprawling web of expensive subcontractors. To bypass this system, he decides to build a new launch provider from scratch in 2002, committing roughly $100 million of his personal capital to the venture. The strategy appears reckless to the aerospace establishment: manufacture the rocket almost entirely in-house. To lead this effort, propulsion engineer Tom Mueller leaves TRCRW, a large, risk-averse aerospace firm, in 2002 to become the first technical hire. Mueller brings a hands-on build culture, having spent years designing liquid propellant engines as a hobbyist. Together, they reject the traditional supply chain, opting to fabricate engines, tanks, and valves under one roof in Hawthorne, California. But translating this philosophy into functional hardware is more difficult than anticipated. The initial timeline targets a first launch in 2003. Instead, development hurdles and testing delays push the schedule back year after year. The calendar slips past 2004, then 2005, before the team is finally ready to attempt their first launch in 2006. In late 2002, a space systems engineer named Gwynne Shotwell makes a quiet, high-stakes gamble. After weeks of hesitation, she resigns from a stable career in the traditional aerospace sector to join a struggling 3-month-old startup. She is hired as employee number 11, taking charge of business development. For Shotwell, the decision is absolute. She privately resolves that if this unconventional venture collapses, she will walk away from the aerospace industry entirely. It is a parallel track of personal risk running alongside the company's technical struggles. By 2008, as the hardware repeatedly fails in the Pacific, Shotwell is leading the commercial front, locked in tense negotiations with NASA for a cargo contract. She is fighting to secure the financial lifeline that SpaceX needs to keep launching, turning a wild engineering experiment into a viable business before the cash completely runs out. On March 24, 2006, the first Falcon 1 lifts off from Amalek Island, rising on a column of fire. The rocket climbs steadily into the Pacific sky for 25 seconds before the flight path begins to warp. Inside the engine bay, a standard aluminum B-nut on the fuel pump inlet pressure fitting fails. Constant exposure to the salty sea air has caused subsurface intergranular corrosion, a structural decay completely invisible to the technicians during pre-flight inspections. The cracked nut triggers a high-pressure kerosene leak, spraying fuel directly onto the hot Merlin 1A engine nozzle. The fuel ignites instantly. As the fire spreads, the main engine loses pressure, and the vehicle tumbles out of control before plunging back down. It crashes into the ocean, just miles from the launch pad. The impact destroys the entire mission payload. Falconsat 2, a satellite designed and built by cadets at the United States Air Force Academy to study space plasma. In the wreckage, investigators and military review boards trace the catastrophe back to that single $5 component. The underlying design of the engine, the rocket structure, and the guidance software remains valid. The failure represents a hard lesson in hardware quality control rather than a conceptual dead end. The physics of the vehicle work, but the execution must be flawless. On March 21, 2007, the second Falcon 1 stands on the launch pad at Omelek Island. When the countdown reaches 0, the rocket ignites and climbs steadily into the sky. This time, the first stage performs flawlessly. Stage separation is clean, and the Kestrel second stage engine ignites, pushing the vehicle into the vacuum. Falcon 1 becomes the first privately developed, liquid-fueled rocket to reach space. In the control room, early telemetry suggests a path to a stable orbit. For a brief moment, it looks like the gamble has paid off, but at 4 minutes and 20 seconds into the flight, a subtle, rhythmic vibration registers. A circular coning oscillation begins in the second stage, a dangerous wobble that grows with every passing second. The rocket's guidance system fights the unstable motion, but the oscillation feeds on itself, shaking the vehicle with increasing violence. At 5 minutes and 1 second, the telemetry screens go completely blank. The signal is lost before Falcon 1 can secure its orbit. A rapid, early failure like the first launch is easy to categorize as a clear miss. A near miss is different. It is far more painful to watch a machine function almost perfectly, only to watch success slip away at the last possible moment. The collective confidence that survived the first crash begins to thin. The goal was visible, and then it vanished. On August 3, 2008, the third Falcon 1 stands on the pad at the remote Kwajalein Atoll. This mission is no longer about refining a prototype. It is a high-stakes deployment carrying active NASA technology demonstration payloads alongside a Celestis memorial capsule with the cremated remains of more than 200 people. The rocket ignites and climbs steadily into the Pacific sky. But during stage separation, the physical realities of the new Merlin 1C engine disrupt the sequence. The engine relies on newly designed regenerative cooling. When shut down, residual fuel vaporizes, creating an unexpected, lingering thrust. It is a tiny pressure transient, but it is enough to push the first stage directly forward. It collides with the second stage. The collision completely destroys the entire vehicle, resulting in a third straight payload loss. With this crash, the project shifts from a difficult engineering task to a struggle for corporate survival. The founder had budgeted for exactly 3 launch attempts, and this was the third. The capital is gone. Simultaneously, his separate electric vehicle company, Tesla, is running out of cash, draining the exact same shrinking, vulnerable personal fortune. The financial pressure is absolute. He later describes 2008 as the worst year of his life, admitting he woke up on the Sunday before Christmas thinking he was on the verge of a total nervous breakdown. The commercial fallout is immediate. Satellite customers vanish, unwilling to risk valuable payloads on a vehicle that has never reached orbit. The next attempt, if the company can even scrape together the funds, will have no paying customer. The fourth flight is reduced to carrying only a dummy mass simulator, a static, non-functional 165 kilogram block of metal, because nobody trusts the rocket with anything of real value. The telemetry from the third flight holds the answer, buried in the high-frequency pressure data from the Merlin 1C engine. When the propulsion team analyzes the shutdown sequence, they discover that the cause of the collision is almost embarrassingly small. The issue stems from timing rather than structural or guidance failure. The newly designed Merlin 1C engine uses regenerative cooling, circulating liquid fuel through the outer walls of the nozzle before combustion. But this design introduces a physical side effect. When the command to shut down is issued, residual fuel remains in those cooling channels. This leftover fuel continues to vaporize, creating a minute, lingering transient thrust that persists after the engine is shut off. On Flight 3, the two stages separated a fraction of a second too early. The first stage was supposed to drift away passively. Instead, powered by that faint, unprogrammed breath of residual thrust, it surged forward and struck the second stage. The hardware does not need a complete redesign. Survival depends on a tiny sequencing change. By inserting a delay of roughly 1.5 seconds into the separation sequence, the first stage will have enough time to exhaust its remaining pressure and fall away safely. A delay of 1.5 seconds is all it takes. On September 28, 2008, the fourth Falcon 1 stands on the pad at Omelek Island. At 22:30 UTC, the Merlin 1C engine ignites, lifting the 68-foot rocket into the Pacific night. Thousands of miles away in Glasgow, Gwynne Shotwell, the Vice President of Business Development, is on the phone inside a hotel bathroom. With the shower running to mask her voice and keep her sleeping husband undisturbed, she finalizes the pricing for the NASA cargo bid. The future of the company hangs on this call and the machine currently climbing through the upper atmosphere. Back in the sky, the first stage burns through its fuel. At stage separation, the newly engineered sequence executes. The system pauses, holding for the updated 1.5-second delay. It works exactly as designed. The first stage falls away cleanly, and the Kestrel second stage engine ignites, pushing the dummy mass simulator into a 667-kilometer circular orbit. With this successful insertion, Falcon 1 becomes the first privately developed, liquid-fueled rocket in history to reach Earth orbit. On 2 continents, within the same hours, the technical breakthrough and the commercial negotiation secure 2 halves of the same victory. This narrow escape cleared the path for Falcon 9, booster reusability, and Starlink, leading to the 2026 public offering. Yet, as the company enters the public market, one question remains. Does its massive valuation reflect actual operational strength, or does it rely on investor faith in an unfinished future? For more stories about the companies that quietly changed the world, subscribe to Architects of Tomorrow. On December 23, 2008, NASA awards SpaceX a $1.6 billion commercial resupply services contract to haul cargo to the International Space Station. On paper, it is a staggering sum for a startup that has launched exactly 1 successful mission. In reality, the agreement is built on a massive leap of faith. The medium-lift Falcon 9 rocket and the Dragon cargo capsule, which the contract relies on to carry out these missions, do not yet exist in finished form. They are mostly blueprints and ambitious promises. This award is not a coronation or a guarantee of future dominance. It is an emergency cash injection that prevents immediate liquidation. The contract does not secure the company's ultimate success, nor does it prove their technical philosophy is correct. Instead, it buys something far more valuable for a young aerospace company on the edge of ruin: the financial runway to keep trying. The financial buffer of the NASA cargo contract allowed Falcon 9 to move from paper schematics to physical hardware. This larger vehicle formed the basis of a shift toward complete booster reusability. In December 2015, a returning first stage touched down on solid ground at Cape Canaveral, proving the concept of rapid recovery. By May 2020, Crew Dragon carried NASA astronauts to the International Space Station, restoring domestic orbital flight to the United States. Soon after, the launch manifest filled with thousands of Starlink satellites, creating a global communications network in low Earth orbit. In February 2026, the company absorbed the founder's separate artificial intelligence startup in a $2 billion all-stock transaction. When the firm went public on June 12, 2026, it debuted with a headline valuation of $1.77 trillion. Yet, analysts immediately questioned if this massive figure reflects actual operating strength or if it relies on investor faith in an unfinished future. On June 12, 2026, the private space startup that once faced total ruin went public at a valuation of approximately $1.77 trillion, marking the largest initial public offering in history. Gwynne Shotwell, the former vice president of business development, now serving as company president, rang the opening bell at the New York Stock Exchange. Yet, the debut immediately sparked a sharp financial debate. Skeptics questioned whether this massive valuation was justified by the current profitable launch and satellite network, or if it instead relied on speculative future ambitions like orbital data centers and a Mars colony. Analysts at Morningstar argued that the firm's true intrinsic value was actually less than half of that initial public offering target. Ultimately, the unresolved question is whether the public market is rewarding established operational strength or simply betting on an unfinished future. Today, SpaceX dominates global orbit, valued at hundreds of billions. Yet, this staggering valuation relies on a still unfinished future of Martian colonization and global networks. The ultimate question is whether we are funding a proven operating giant or merely the same audacious faith that once barely saved them from bankruptcy. Subscribe to Architects of Tomorrow for more stories about companies that quietly changed the world.